Hello, favorite pre-calc class. I am going to make you guys a quick video. I'm just going to go over just a couple problems that I thought were worth doing. Hopefully it'll be enough, though, to just give you kind of a jump start to remember what you need, especially if it's been a couple days after some snow, which we are hoping for. So, that being said, I'm going to start with number 3. For vertical asymptotes, we're looking for where our denominator is a 0. So if I were to factor my denominator, so I have x cubed plus 3x, we want to know where that's going to be 0. I'm going to pull out an x, which leaves me with an x squared plus 3. Well, this thing here can never be 0, because if you square something, it'll always be 0 or positive, right? And then you're adding 3, so that won't ever be 0, but this can have a value of 0, so my vertical asymptote is going to be at x equals 0. Let's think about our horizontal or slant asymptote. Well, the degree in the numerator is bigger than the degree of the denominator, so that lets me know that there's not going to be a horizontal asymptote, but there can be a slant asymptote if the degree of the numerator is just 1 more. Well, notice this is a degree of just 1 more, so that means I have to do long division. So I'm just going to do it right here. So I'm going to have x cubed plus 3x all into 3x to the 4th plus 4, but you'll notice that there's a lot of terms missing in here, so I'm gonna put in some ghost terms. Okay. Well, x cubed is going to go into 3x to the 4th x times. Oh, sorry, 3x times. So when I multiply it out, I get 3x to the 4th. When I multiply this out, I get 9x squared. Well, I'm going to line that up with my x squared term. When I subtract, those will go away. When I subtract, I get a 0x cubed. When I subtract, I get a minus 9x squared. I'm going to drop down my next couple of terms. I don't really have to because it's 0x, but I can. So now I'm going to keep going. I'm going to see, does this term here go into here? Well, you'll notice x cubed isn't going to go into the x squared, so there's not going to be any more terms. But this is going to be my remainder. Okay. Your slant asymptote is going to be just the linear portion of your long division. So this thing here. So my slant asymptote is going to be y equals 3x. Okay, I believe that's the only one with a slant asymptote on the sheet, and then you make sure to check the answers to, there's a key already up on Blackboard. So you can check the other ones later. Let's move down here. Number 9. So remember, we have a couple places where we're going to have a problem with our domain. So some of the problems is when the denominator is 0, which could be a vertical asymptote or a whole. We have problems when we have a negative under a radical. I think there's anything else off the top of my head. Those are kind of the big ones. So when I see this, I notice that I have a radical. So I want to see if this can be negative. So I'm going to start by factoring this under here. And you'll notice if I rewrite that, I'm going to get the square root of x minus 1 squared. Now I know that squaring and square rooting, they're inverse operations, so in a sense they undo each other, but if I look at my original function, I have to deal with this as is. I need to see if there's ever something negative underneath. Well, because I'm squaring something, this is never going to be negative, because no matter what I put in for x, even if the stuff in the parentheses is negative, when I square it, it'll become positive, so that's not a problem. But I can't have 0 in the denominator, and the only thing that's going to make the denominator 0 is when x is equal to 1. So that tells me that x cannot equal 1. So now when I do my domain, I'm going to say, okay, I'm going to go from negative infinity. I use a parentheses because infinity is not a value that I can include. It's saying go all the way up forever and ever and ever, or down, I guess, forever and ever and ever. Go to 1. Don't include it because we have a problem at 1. Then start back up start back up after 1 again and go to infinity. So there's number 9 for you. Okay, next I'm going to do a graph. Remember, the y-intercept is when x equals 0. So if I plug in 0, I'll get negative 2 over 1. So my y-intercept is going to be when x is 0, y is negative 2. The x-intercept is when y is equal to 0. Well, you'll notice well, the numerator is never going to equal 0. And even if I made the denominator 0, I'd be dividing by 0. That's no good. There's not going to be any x-intercept. And you'll kind of see why in a second. Vertical asymptotes is my denominator, the value of x that makes my denominator 0. Horizontal asymptote, you'll notice my denominator has a larger degree, which means my horizontal asymptote will be when y equals 0, which makes sense now why I never crossed the x-axis, because here's my horizontal asymptote. My vertical asymptote is here. Okay. I know that I have a point at 0, -2. So now I'm going to plug in a couple more points. I want to do at least 2 per section. So I'm going to do one at -2 here. And then I'm going to go at 2 more, -4. I don't really care which 2 points you pick. I like to space them out a little bit. I think it gives me a better picture of what my curve looks like. Then I'm going to do one at 2, or I'll do one at 0 because I already have it. And then I'll go over 2 and do another one. I've already done this, so I'm just going to put in what I got really fast. This is 2/3. This was 2. This was -2 and -2/3. You're not necessarily going to have a calculator, though, so you need to be able to plug these in by yourself. So essentially all I did is I said, okay, for -4, I put that in here. That gives me a -3 in the denominator. -2 divided by -3 was 2/3. That's where that came from. So -4, 1, 2, 3, 4, 2/3. -2, 2, 0, -2, 2, and then -2/3. Okay, and then I'm just going to connect my graph. Oops. Not my best, but it will work. Okay, so there's my graph for number 10. Okay, sorry, I was just looking at that again. Okay, number 12. It says, use what you know about rational functions, asymptotes, and the points plot on the graph to write a function that represents the graph. Okay, well, let's look at what we know. We know we have 2 vertical asymptotes. They're at x equals -2 and x equals +2. Well, that's telling me what my zeros in the denominator are. So if I look at my denominator, I know that I'm going to have this. Or if you prefer, you could also leave it like this. I also know I have an x-intercept at 0, 0. Okay. Which means in my numerator, I'm going to have a factor of x. If you look, you'll also notice that at this 0, it hits and it turns back around. That means that this is going to have a multiplicity of 2, or my factor of x is going to have a multiplicity of 2. Let's see if there's anything else. You'll notice we also have a horizontal asymptote at y equals -1, which means the degree of the numerator and denominator has to be the same. Coefficient over the coefficient. If it was y equals 0, I would know that the denominator had to be bigger. So if I start writing this out, I'm going to get f of x is equal to, now if I didn't notice this multiplicity of 2, this is what I would have put. But you'll notice this is telling me that the denominator and numerator's degree has to be the same, that I need to have another term up here. Well, since there's no other zeros, that would also give me an indication that this same factor is going to have to be used twice, have a multiplicity of 2. So there is my function. Oop, I missed one more thing. See if you guys can catch what it is. I'll give you a hint. It has to do with the fact that the horizontal asymptote is -1. So you'll notice the ratio of the leading coefficients is something divided by something, but it became negative, right? Which means one of my leading coefficients has to be negative. So I threw that negative in there. Okay, so there's my answer for that. Let's keep going. Number 13. We need to figure out what values of x satisfy this. So if I were to distribute, I would get this. I'm going to subtract the 20 on the other side. There we go. If I were to factor that, I'm going to get an x plus 5 and an x minus 4. Okay. These are both zeros. If I plug in something bigger than 4, this will be positive and positive. If I plug in something like 0, positive, negative. And if I were to plug in something less than negative 5, I'd have negative, negative, which multiplies to a positive. So I want to know when my function is greater than 0. Well, it's greater than 0 from negative infinity all the way up to negative 5, and then starting up again from 4 to infinity. Okay. For number 15, I need to subtract the 1 over. But I need to have a common denominator so that I can subtract the 1. I'm going to rewrite this as x minus 4 over x minus 4. So if I have an x plus 2 minus x plus 4, I'm distributing that negative. I'll be with a 6 left over in the numerator and an x minus 4 in the denominator. That all has to be greater than or equal to 0. So now I can do my number line. 4 is going to be my only 0. Oops, sorry, it's not a 0. It's going to be undefined because it's what makes my denominator 0. If you test some values, that should be what you get for your number line. I want where it's greater than or equal to 0. I can't include 4, so there's no zeros, but it'll be bigger on this side. So I'm going to start after 4 and go all the way to infinity. Okay, let's see if we can do 2 more problems really fast. So solve the following partial fractions. Well, let's start by factoring, and if I factor this, I end up with an x plus 3 and an x minus 2. And we said, okay, well, we can rewrite this as a over my first factor plus b over my second factor. Because I have non-repeating linear factors, we can use our Heaviside method, which just says we're going to isolate. So, for instance, if we want to do a first, we want to look at when its denominator is going to be 0. Well, negative 3 will make its denominator 0. I'm going to cover up that factor because it's going to be a 0. We can't divide by 0, so I cover that up and plug in negative 3 to everything else. So that's going to give me 5 over negative 5, which gives me a value of 1. So a equals negative 1. And I like to mark it so I can find it easily. Now let's do b. The value that's going to make its denominator 0 is at x equals. So I'm going to plug that in, but ignore that term, that factor it came from. So if I plug in a 2, I'm going to get 5 over 5, which is equal to 1. So b has a value of 1. So my final answer is going to be negative 1 over x plus 3 plus 1 over x minus 2. So remember, the purpose of partial fractions is to take a fraction that's pretty complex and turn it into 2 simpler fractions. If you were to add these together, and if you were to create a common denominator, you would end up, the sum would give you this. Okay, so remember, we just use the Heaviside method. It's the shortcut, and it only works when you have non-repeated linear factors. So these are not the same, they're non-repeated, and they're both linear. Now, let's do a trickier one. Before we do number 22, though, remember for number 20, you'll notice the numerator is a larger degree than the denominator, or even if it was the same degree, you have to do long division first. Okay, so if the degree is the same or bigger, do long division first. Okay, and all my work for that is on the key on Blackboard. But let's do 22 together really fast. When I square this, this is going to give me an x to the 4th times x, which is an x to the 5th. So this denominator is has a larger degree than the numerator, so we don't have to do any long division. Let's start separating this out. So I'm going to have an a over x. This is a linear term, so it's just going to be a constant in the numerator. Then my next prime quadratic factor is x squared plus 3. Because I have a quadratic in my denominator, I'm going to put a linear in my numerator. Because this is a repeated factor, I increase this degree by 1, but because the factor itself is quadratic, I'm going to use another linear numerator. Okay. Well, if I want to solve, and this method works for everything, we're going to multiply everything by the huge, the denominator we would get if we add these together. This is my common denominator. So I'm going to multiply by x squared plus 3 all squared. Well, when I do that, this dividing, this multiplying, they're going to undo each other. They're multiplicative inverses. I think that makes sense. I know we talked about that in class, but yeah, multiplicative inverses. So this is going to, when I multiply this by all of this, I'm just left with my numerator. Oh, I hope this all fits. Then when I multiply this by this term, the x's will cancel out, but I'm still going to be left with an x squared plus 3 all squared. And I multiply this whole term by this. One of the x squared plus 3 terms are going to go away. But I'm still going to have an x and an x squared plus 3. And then my last term, all I'm going to have is an x left. So dx plus e times x, that'll give me a dx squared plus ex. Okay, so if I were to rewrite this, this whole thing is going to become x to the 4th plus 6x squared plus 9 plus, let's see if we can get some of this straightened out. I'll just write it like this for now. Let's distribute that x just to this. Okay, so that's going to give me an ax to the 4th plus 6x squared, plus 6ax squared plus 9a plus, okay, let's have some fun, bx to the 4th plus 3bx squared plus cx cubed plus 3cx plus tx squared plus ex. Okay. Well, now I'm going to combine terms. So I have an x to the 4th and x to the 4th. So that's going to give me an a plus b x to the 4th. So I've used that. I think I only have a cx cubed term. I have a 6a plus 3b plus d x squared term. Then I have a 3c plus e for my x term, and then I just have a 9a left over. Well, the nice thing about this is some of them are going to be pretty easy. Let me write this back in really fast. Well, notice my constant term, 9a and 18, that's going to make a2. Let's see what else we can do quickly. Well, c is my x cubed term. C is going to have to be 0. Let's look at this one. Well, if c is 0, all we're going to be left with is e. So that means e is going to have to be 8. Okay, a plus b has to be 3. So if a is 2, b has to be 1. Which means we're left with d. And I believe if you substitute in here, you'll eventually get d equals negative 11. Okay. So for my final answer, I'm just going to rewrite. So I have a over x, so 2 over x. bx plus c, well, b was 1. There's no c, so we're just going to do x over x squared plus 3 plus dx plus e. So d was negative 11, e was 8. And that's all going to go over x squared plus 3 quantity squared. So there's your answer. So hopefully this was helpful, guys. I'm sorry it was kind of quick. But next time I see you guys, we'll be taking a quiz on this, okay?